Okay, this is lecture 22. So the previous lecture we finished by proving that click requires, at least n to the small o of k time under ETH. Okay, and using this, we get a long list of other problems, more or less straightforwardly, that have similar lower bounds. So, I'm going to skip over this and do the more interesting stuff for me. So we want to prove some lower bounds for some geometric and planar graphs problems. So the first problem we are going to look at, it is a bit weird, to put it mildly, and grid tiling. It's called grid tiling. So okay, so in the grid tiling problem, what we have a set of labels, right? So we're going to have a grid of size k by k. And for every cell in this grid, let's call it ij, we're going to have a large set of labels, sij. And the important thing is that this set of labels are not just going to be numbers, they're going to be element of the two-dimensional grid n by n grid, right? So we're going to have this grid. We have two grids, right? One is the underlying grid, which is k by k, and then for every grid cell we have a list of labels which are also a grid. And now the problem asks in the grid tiling, is there a way to choose pairs? You have to choose for every node in the k by k grid, you have to choose a label from this set of labels. And you have to choose a label such that they all agree every column has the first coordinate in all the labels you choose, right? So, so think about if you want for every point you choose two colors that belong, a pair of colors that belong to Sij, and what we require is that every column, the first color agrees, so all the columns have the first color in the first row, and then what we ask is that every row, the second coordinate of the labels agree, right? So let me choose it, right? Every here one, the second label agree, right? So it's kind of a very mysterious problem. It's a bit strange, right? So again, we have k by k grid. Every grid cell have a list of points in the two-dimensional grid. And now we have to choose for every grid point in the smaller grid, we have to choose a label such that a label is just a two-dimensional grid from this bigger set of labels that is allowed. And we have to choose them in such a way that every column, the first coordinate is the same of the labels, and every row, the labels are the same. Okay, so this is the grid tiling problem, which is a bit artificial, but it's going to be convenient for reduction. And the claim is that this problem is as hard as grid, as far as the complexity, where the parameter k is, of course, the size of the grid. Okay, so the claim is that under ETH, grid tiling is W1 hard, and you cannot get better than, you cannot get an algorithm with tiling time n to the small o of k for it. And the proof is, the regular kind of NP completeness proof that requires a clever trick. So we're going to do reduction from click, of course. Okay. So we're given a graph G and a parameter k. And the question is there a click of size k in this graph? And the reduction is going to be, we are just going to create this underlying clique of size k by k. And we're going to first look on the diagonal elements. Okay. And on the diagonal elements, we're going to put a very special set. So SII, this is just going to be all the pairs that have both coordinates equal. AA, sorry, let's call it, yeah, AA, over, where A goes over all the vertices of the graph, the original graph. Okay. So before telling you what I'm going to choose for the other cells of this grid, notice that since I have only those sets, you essentially have to choose one of them for every one of those, you have to choose essentially for the diagonal, for every element of the diagonal, you choose one vertex in the graph. Okay, so you choose one vertex here, and you might choose some other vertex for this cell. Now, the important thing to observe is because there is a feasible solution, the feasible solution would require that all the elements on its row must have the same, let's assume that we chose A here, right? All the elements in this row must have A in their first coordinate. Similarly, in this column, if we chose here label B, then the second coordinate here has to be B, right? Now, the idea is that we are allowed to choose, we can write A, B here only if the vertices A and B have an edge between them, right? So that's the only requirement, right? Now, so as such, for all the cells that are off diagonal, Sij, such that I is not equal to J, I'm going to set the edges to be alpha beta, where alpha beta is edge in the graph, in the original graph. Okay. Now let's see, and this is the reduction. The claim is that there is a valid tiling of this grid if and only if the original graph has a clique. Okay, so I essentially kind of almost did the first part of the proof of correctness, right? Because let's assume that for two elements of the diagonal, I had chosen the same label. So by just the argument I just said, the cell that belongs to the same row and column would have to have the same label, but all the cells that are off diagonal never have the same label in both coordinates because the graph doesn't have loops, right? So this immediately implies that on the diagonal, we must choose k distinct vertices, right? We must choose k distinct vertices, and furthermore, for every pair of those distinct vertices we picked, again, the cell that is the intersection of the row and the column forces us to, it's allowed this choice if and only if this edge is in the graph, right? Which means that there is a valid tiling if and only if there is a clique of size k in this graph, and that's the end of the proof. The other direction, of course, is immediate, right? If there is a valid tiling, then there is a clique in the original graph. Okay, so this is, an easy thing to prove. Let's move on to the next problem, which the books speak about it earlier, but I skipped it, so I need to now define it. But in fact, we essentially saw something very similar for it just right now. It's in fact reasonably popular if you look on graph coloring problems. So list coloring, I give you a graph as usual, and now for every vertex I give you a list, right? So there is a vertex V, and I give you a list L of V, which is a list of all the valid colors that I allow to this vertex, right? This would be a list of colors, 1, 2, 17, right? So you have a list of colors, and this would be U, there would be a list of U, and the task is to find the coloring of the graph, valid coloring as usual, where the label, the colors you choose, you're allowed to choose a color only if it appears in the list of allowable colors, right? So So clearly this is an extension of regular coloring and the problem is NP complete. But you know, potentially it might be much harder, right? Because you're adding more constraints. Okay, and in particular, people are interested in the question of, you know, how big does the list have to be such there is always a valid coloring, right? So yeah, and you know, and observe that, you know, so this problem is a bit weird, right? For example, if I find the valid coloring of the graphic, the list colors might just be for every vertex the color in the coloring. So there might be a valid coloring of the list even if every list is of length 1, right? Which is very weird and counterintuitive, right? So as I said, there is quite a bit of research on it in combinatorics, and we would like to claim that this problem is hard. Okay, so formally the claim is the following. The claim is that if I give you a planar graph, which is an instance of list coloring, and this planar graph has tree width t, then there is no, the problem is that W1 are hard and cannot be solved in time better than, you know, n to the small O of t under ETH, right? And the reduction is exactly what you expected. We're going to do the same reduction we did before into this t by t grid, right? Instead of k, we're just changing the letter. So we have this t by t grid, and for every one of those cells, we have this list, you know, cell ij. We're going to have the list sij, as we specified in the previous reduction. Now, what is less trivial is how do we force that, you know, all the nodes in one row would have the same first column, right? So to this end, what we're going to do is that for a set S, two adjacent vertices in this small grid that are adjacent, Si minus 1, Si minus 1j, every two cells, we're going to create this fan, right? We're going to create this large number of vertices, parallel, essentially parallel paths that connect those two adjacent vertices, right? And here's what we are going to do. We are going, the lists for all the vertices here are going to be the following. For any, so let's see how to say it. For any AB and A prime B prime, such that A and A prime are not equal, right? So for every pair of numbers that are not equal, here A and B are from the grid n by n. Okay, so this is from the big grid, right? So we are taking those pairs from the big grid. For every such pair, such that the rows are not equal, we add, we create a node with label that the list of colors is A, B, and A prime, B prime. Okay? So that's what we do, right? We do it for, right? We do it for all those nodes in the middle. Okay. Now let's see why this forces things to be, forces the labels to be equal. What happened is that this vertex Sij, we're going to choose a label. Let's say call it alpha, beta, right? Now, all those vertices here in the fan in the middle, they cannot take a label that is equal to alpha, right? So what happened is that all the pairs that have alpha in them are forced to take a different, are forced to take the other pair, the other color, right? This means that for the vertex here, the vertex on the other side, this vertex on the other side of the grid, the only label that is left open is one that the first coordinate is alpha, because the fun vertices used in the first coordinate, they used all possible labels except the ones that have alpha in them, right? So this vertex must choose a label that is alpha. So this constraint forces that all the rows, each row in this list coloring, are going to have in the first column, they're going to have the same label, and you repeat the same trick for every column, right? For every column, you're going to also build this fun thingy. Okay, parallel path. So the resulting graph is a bit weird, right? It's essentially this grid where instead of grid edge, we have all those parallel edges, and it's going to be a T by T, or if you want a K by K grid. But it's not hard to see that this graph is essentially has the same tree width as K by K grid, and in particular it has tree width K, or tree width T, right? It's the same parameter. So we got this graph, this weird graph, this grid with a lot of parallel paths for every edge, and which has tree width T, and there are list colors for every vertex, and this graph has a valid list coloring if and only if there is a clique of size T in the original instant, or K, right? So that's it. That proves the hardness. And of course, showing that the reduction work in the other direction is immediate, right? If there is a valid list coloring, then exactly as in the previous proof, we can argue that this results in a clique of size T in the original graph. Okay. So that's nice. Okay, the next problem we want to look at is back to grid tiling. But now we add, this is grid tiling with smaller equal. Here what we require is that the labels in every columns are not necessarily equal, but they have to be monotonically increasing, right? So they have to be increasing in the first coordinate, they have to be monotonically non-decreasing in the first coordinate, they have to be monotonically non-decreasing in the second coordinate in the grid. It's again, you have a grid, you have for every vertex you have a list of labels where the labels are taken from a two-dimensional grid, and now you're just, instead of the equality condition we had before, we just require monotonicity, and this problem turns out to be also W1 hard. The book has the proof of this hardness. It's a pretty, it's the usual NP complete time reduction where you have to use gadget carefully and so on. I decided not to cover it. You can read it in the book if you're interested. Okay, the next problem of interest is scattered set, which is a useful problem to know about. So scattered set asks, I give you a graph and a parameter D and of course K, and I ask, is there a set of K vertices? There a set of K vertices such that so let's call it C, the subset of the vertices of the graph, such that for first, of course, C has to be of size K, and the second requirement is that for every two vertices in the set C, the distance in the graph, here we're speaking about just, distance under unit cost, is at least this parameter D, right? So this is this problem. And of course, for D equal 2, this just asks for independent set. Okay. So not surprisingly, this problem is, at least as difficult as independent set. And in particular, we can now study it on planar graph. So on planar graph, one can show, this is theorem, right? Scattered set on planar graphs can be solved in n to the square root k time, right? And that should not be too surprising, right? So, you know, this somehow have to use planar graph separator and so on. It's not an immediate algorithm, so I'm not going to go into the details of how it works. In particular, it's not described in the book. But the nice thing is that we can prove that this is tight under ETH, right? So the theorem. By the way, this algorithm works by, guessing essentially the separator in the optimal solution in the Voronoi diagram, and then recursing. It's very similar to, some recent work about, on quasi-polynomial time approximation algorithm for some clustering problems. So let me not go into that, how it's being done. But the interesting result, as I said, is that in fact, this is tight, right? You cannot do better than n to the square root of k under ETH. And the proof, unfortunately, is this reduction from grid tiling with smaller equal. And the proof is pretty tedious. So again, I'm going to skip it. I don't think it's sufficiently interesting to cover it in detail. Okay, the next problem I want to talk about is unit disk independent set. And again, the basic problem is I give you a set of disks in the plane, set of n disks in the plane, set of n disks in the plane, unit disk, right? So n unit, right? Unit radius, right? They're all of the same radius, unit disks in the plane. And we have a parameter k, as usual, k. And the question is there a subset of k disk, a subset of k disks that is independent, that such that they're independent, which means that no pair intersect, no pair intersect. Okay, so as usual, it's not too difficult if you know the machinery to show that one can solve it in n of square root of k. This is essentially what you need to do. You look on the optimal solution, you look on the power diagram. This power diagram has k cells, so there is a separator of size square root k. You guess these separators and you recurse. It's a cycle separator. So, blah, 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 5 pages later, and it goes. It's one of those very tedious algorithms. But the nice thing is that this is tight, right? So you cannot do any better. So this is theorem 1424. Under ETH, independent set of unit disk cannot be solved in time better than f to the k and to the s omega of k, right? And of course the problem is attached. Sorry, the problem is WR. Problem is W1 hard. Yeah, so right, so that's pretty nice. Again, the reduction is pretty tedious. I'm not going to do